Hello and welcome back to Calculus 3. This is section 12.9, Lagrange multipliers, or whatever you pronounce it. So we're going to take our min-max problems to a next level now. What we found before was a min-max, the saddle point for a shape, and that was the end of the story. Now we are going to find the min and max for the shape that is that has a constraint. Now let me put that in the eyes of Calculus 1 first, in the context of Calculus 1. So what I'm going to do is say we want to find two numbers, x and y. Now this is Calc 1. So find two numbers x and y such that, let's say, their sum is, I don't know, 30, and the product is max. Right? So sum has to be 30 and the product is max. So when you're looking at this problem, you see you have two equations. Now, if I have equation which says xy equals 6 or 30 or whatever, I can unleash the derivative upon it and find the maximum for that function if it exists. But the interesting thing here is that there is this constrained function. So I'm not interested in solving this problem because that's completely irrelevant to what we want to do. What's important is for you to know that you have constraint and objective function. The objective function is what you're trying to find. You are trying to maximize the product of these two numbers. So that's the object of the problem. That's what you have to do. Under the constraint that the sum of those is 30 or 12 or 5, right? So constraint, right, it just really in a sense of English words, right, that are used in those titles. So in Calculus 1, we did not make big deal about these names because, you know, no, not really needed. Now in Calc 3, we are going to make a deal between these, right? And we're going to find gradients for these two functions and set the gradients equal with the help of a parameter, because for these Lagrange multipliers, we know that parallel gradients have the have the constant multiple in terms of gradients. Well, we'll see. Anyway, so what I have here was Calculus 1 review for optimization. That was, I believe, 4.4 section or something like that in the textbook. Now we're moving to calculus. I want to find, and actually I can take this cylindrical object and I will draw on this cylindrical object an ellipse on a side. So let's go, let's say like this. So if you take a look, you see this ellipse, it goes down, and then goes up, and then goes down, right? So I drew the ellipse. So what are you thinking about? Me taking a sword and slicing it like this. So I'm going to draw this object. So this would be your cylinder. And then I'll just say, okay, I have this ellipse like this. So what am I looking for? I am looking for the, oops. I'm looking for a max point or a min point on the shape of a cylinder, but the constraint is that that maximum has to be on the ellipse. So that's clearly this point here. Okay? So I am looking for the maximum of the ellipse, which has to be on a shape.
But you're looking for the maximum of the ellipse or the cylinder?
Of the ellipse. Maximum of the cylinder is the top. Did I say it backwards earlier?
I think so.
Oops, sorry. It's the maximum of the ellipse, minimum of the ellipse, right? And that ellipse is constrained because it lives on the cylinder. That's its universe. This ellipse cannot leave the cylinder because cylinder is all that exists. All right? So that's the beautiful thing about math. You can just, picture one object and there is nothingness.
But is that just because you do it there? When you draw, when you have it like outside?
You can't, because ellipse doesn't exist in the physical reality, like number 7. Circle doesn't exist. Those are two-dimensional entities. Cylinder does. That's real. Look. Real. Right? Try to do that to a circle. Yeah, sure. So, yeah, it's in the realm of the physical existence, right? Now I gotta exercise. And one. Thank you. Well, that's it. I'm done for the week. We're off tomorrow. I'm gonna lay down and wear this off. It's like this is too much. Okay. Now, what's actually happening here with these Lagrange multipliers? So we have the objective function f, which is the one where we look for min and max, and we will have the constraint function g. Both of those will be written in implicit form, and then we will find the gradients. Now we are two-dimensional gradients and three-dimensional gradients, right? So we just write the overall equation that solves these problems. Gradient of f is equal to lambda gradient of g. That's the equation that solves everything. And g of xy, which is the constraint function, equals to 0. All right, so next time someone tells you, what do you know? Just write this equation. You have 3 variables, 3 unknowns, 3 equations. So that will be another equation that you need. Constraint equation. It's a relationship between all of your x's, y's, and z's. Well, it has to live on it. Remember, the min and the max has to be on that equation. It happens on that, whether it's surface or line. Let me tell you what this is. This equation here is this equation. Yes.
Yeah, I don't know what's going on.
That's why we have a storm tomorrow. I'm sorry? The other equation was x plus y equals to 30. So x plus y minus 30 equals to 0. Bum. There you go. And that's exactly what you will be doing all the time in this section. Because equations will rarely be given in this form. You will have to move everything to the left, make it equal to 0, and then unleash the gradient upon it. So let's start with the simplest possible problem to see the procedure. We have this done in 2D or 3D. This is dimensionless, right? The equation. You can do this for any dimension, right? Because gradient is a vector for any dimension. We don't use cross product that constrain us to certain dimensions. So we are, this technically works for anything. And we're going to do a 2D case, right? For 2 variables first and then 3. And then we'll, I hope to be able to finish 2 of those in time. We only have 3 minutes left and then another 30 after that. Yeah.
Technically, it's 3 minutes and another 35.
Yeah. What happened?
You really let us on there. Like, you only have 3 minutes left, and then another 30 minutes after that.
Apparently 35, so I made a mistake. I'm sorry.
Oh, I thank you.
All right, so let's take a look at the first one. We are going to look for these extreme points on xy equals to xy squared with a constraint of x squared plus y squared equals to 1. Nope. Never. Because you will know immediately which one is the constraint. It's a complete equation. I put the air quotes for those listening. Actually, are they listening? Okay, yeah, because we have. I just wanted to make sure the stream is going. All right. So your constraint, and here is the quotation marks again, the complete equation, right? This one is not equal to a number. It's equal to a z, right? All right. So what do we do? Well, what's del f? Partial derivative of x, which is y squared. I know, spring break, right? And then partial derivative of y is 2xy. So that's your del f. Now you have to find your del g. Partial derivative of, oh, first we have to get what's g of xy. It's x squared plus y squared minus 1. Are we all agreeing on that? Awesome. Equal to 0, obviously. So partial derivative of x, 2x, partial derivative of y, 2y. And now we use the equation. Equation says, this is what you're memorizing, right? We have the parameter lambda, that's the Lagrange multiplier. And we don't need that value. So you will try, when you hit the equations, to eliminate that first, because you really don't need it. Okay, so now plug everything in. You have a vector that says vector y squared 2xy is equal to a lambda, and then I have 2x and 2y. Lambda?
My name is Alana, but I like to go by Alana. So some people call me Llama. And my whole name is Alana if you put the 2 N's together.
So how do you spell the name?
A-L-A-N-N-A.
A-L-A-N-N. N-N.
So if you put the 2 N's together, then you would say Alana.
That's not close enough.
But my name is Alana, so this is gonna be the one for Alana.
All right, figure that out.
I'm so glad
it's necessary, okay, a necessary break before I do the most important part for this lecture. And that is, once you have everything in this form, you will separate the dimensions. So we are going to have y squared is equal to 2 lambda x for the red one, and 2xy equals to 2 lambda y. So this was the blue one, and this was the, no, this was the red one and the blue one. Now, confuse my colors. We also have, as a third equation, how many variables do you have? X, y, lambda, 3, right? And you see 2 equations. So the extra equation that we are bringing in, which is a complete equation that we can use, is always that constraint equation, G. The simplest possible case that you can have in these problems is 3 unknown, right? 3 equation, 3 unknown. They are almost always by rule nonlinear. So solve it, right? There are no rules how to solve this. This is literally, you're sitting there for hours if need be to figure out, you know, what the solutions for these are. One of the tricks would be to try and solve both for lambda. First equation, lambda equals everything else. Second equation, lambda equals everything else. And then immediately, lambda equals lambda, make those 2 equations into 1 equation, right, by substitution. And then you are down to 2 equations to unknown. But in some cases, that will make a far bigger mess than if you had some other cool idea. My idea for this particular solution here would be, let me try to say 2 lambda equal 2 and 2 lambda equal 2, and then put those equations together to see what happens, right? So for this particular case, it might work quickly. So from this one, I'm going to say that 2 lambda is equal to y squared over x. And from the bottom equation, 2 lambda is equal to just 2x, right? Because y divided by y is 1. So I have that. And now when I equal these 2 equations, 2 lambda equals 2 lambda, I actually get y squared over x is equal to 2x, from where y squared is equal to 2x squared. Well, that plugs in here, and we have the solution. So we were extremely lucky. This was a joke of a problem, actually. So x squared plus, and instead of y squared, I put 2x squared equals to 1. So that's 3x squared equals to 1, from where I have that x squared is equal to 1/3. And then I have that x is equal to plus minus root 3 over 3. Exactly. Then you will bring that to the equation to find your y's. Now, when you square this, you get 1/3, so that's 2/3. So y squared is equal to, I'll write it for once, 2 times root 3 over 3 squared, from where y squared is equal to 2/3. And then when I have, 2/3, and I take the square root of that, which is clearly root 6 over 3. There I say clearly. Clearly, right? Awesome. So how many points do I get? I have a plus minus on x, plus minus on y. I'm getting 4 points for this Lagrange. hold on. Root 3 over 3, root 6 over 3, root 3 over 3, negative root 6 over 3, root 3 over 3, sorry, negative root 3 over 3, root 6 over 3, and negative root 3 over 3, negative root 6 over 3. Now, I'm happy when you find this. What's the rest of the problem? To figure out if they're min or max. And how we do that? Yeah, you know how to do that from previous lecture. Partial. Do you have to go and find fx and equal to 0 and fy equal to 0 and solve that?
No.
Hell no. You already have the point, right? What do you do? fxx, fy, just go from f, find those, grind through. Will I ask you to do that in a problem? Well, no, because you will have separate problem from 12.8 to do just that, and then you will have Lagrange, which does the same thing with the constraint. So you will write not to double up on a very busy work. You know what I mean? And you're welcome. Yes.
So the formula del f equals lambda del g.
Yeah.
Where does lambda come from?
Lambda is the multiplier because what's happening here is the the lambda is the multiplier for Lagrange multiplier, and what it does is the parallel gradients are constant multiple apart. That's all it says. Parallel gradients are constant multiple apart. So when you are looking, remember that the tangent planes, right? Tangent planes are always horizontal when you have min and max, right? Anytime you have a maximal value, like right here, it's going to be a tangent plane. I talked about graduation hats, right? Now you know the tangent plane to the knowledge you got that. So, come on, 99% of graduates do not know that. Guess who will? That's why you should walk with everyone else there. That's why business degree, do you know what's happening? Can't say that to myself on the phone. So, yeah, you have the tangent plane, right? For the max is always horizontal. For a min, right here, also horizontal, right? And they're going to be constant multiple apart in terms of their gradient. That's the lambda. We don't need to know the value for that. Sometimes it will be necessary for you to compute the value for lambda, like, I don't know, root 2 over 7. And then plug that back in and work out the rest of the problem. It's rarely, I think I ran into maybe 2 or 3 problems so far, you know, when students ask random questions from homework or something. It's very rare that you have to actually figure out lambda first and then find other things, because lambda is not needed for anything because this is what we are looking for, right? So if you can eliminate lambda in a first shot, that's what you do. Yes?
Quick question about the planes. You said that when they max and min, the tangent is parallel. Okay.
And when we're finding big D, right, we go back to get f of x. We're going back to the
F.
f of it, yeah, not the constraint, right?
Not the constraint. Not the constraint. It's the f, because f gives you the shape of the entire object. F is the shape of the object. G is the constraint from the domain that says, look along this line where stencils for cookies, okay? So you have a dough in front of you, all right? Think of like a pizza dough, and you take a stencil for cookie. That is your domain. You are holding G of X in your hand, G of XY. And when you push, now imagine that dough on top is not flat. it's going to have min and max everywhere, right? So when you press that into the dough, right, that edge of the dough that is touching the stencil will have min and a max and a min and a max. That's what it detects. Those min and max on the curvy path of a stencil. Now, what kind of stencils do you have? You have a circle stencil, like one we had here. That stencil was a circle, like square plus y squared was your unit circle, right? 1 inch stencil, so 2 in diameter, right? And just imagine the dough from the inside of the stencil along the wall of the stencil. It's not a flat thing. It's going to have little bumps here and there. Those max and min along the stencil of the dough are at these points. So that's what it detects. If you want any min and max inside the stencil, inside the dough, 12/8, all right? Fx equal to 0, Fy equal to 0, and crank that part. This detects only the edge when the edge is all wavy and right. So it's a circle, and then you get creative. Maybe it's a 4-leaf clover. Thank you. Whatever, right? A paw or whatever it is.
So to determine what type of variable point they are, you still have to come up with the
D. Mm-hmm. So
you would just do that with your f of x, which is like
yep. So min max, go do D. 12.8. All right. So that solves, that ends the problem actually. Awesome. Now, 2 minutes left, and then another 20 after that, so we can squeeze in a 3-variable problem. Are you okay? You will make it. It shouldn't be that difficult. For you. Um, 16, 18, 20, 22. Actually, 22 is, we don't have time for it. 16, okay. There we go. Hold on, you didn't see the constraint. You have to be, and then it's equal to 9. You know what to do. First, make that one into G equals everything else. Get these guys to put them in del F. Get the G guys to put del G equivalent together. Just get two equations, okay? Get two equations.
So,
What?
you said this would give me money.
Where's my money?
Where's my money?
Where's my money?
Wait, what? What did you say?
He asked where his money.
Yeah, what was your response?
Stay safe.
You were.
What did you think?
Of course you would.
But not.
So I hope you have all of the partial derivatives, fx, fy, fz, gx, gy, gz, which creates del f, del g, and then you equal fx lambda gx, fy lambda gy, fz lambda gz. That actually takes a lot of mental power to say. Damn. I'm tired, but that's okay. Class ends in 3 seconds, and then other 15 minutes after that. I know, it's awesome. It's del f, lambda, del g. All right, so what do I get? YZ, oops, YZ, XZ, XY equals to lambda 2x 4y.
No, nobody wants to see the dog.
It's on middle.
All right, so I hope you guys have the same equations. I have YZ is equal to 2 lambda x. XZ is, who picked this problem? 4 lambda y. And, oh, we have a volunteer to solve this. 8 lambda z. And we also have a constraint x squared plus 2y squared plus 4z squared is equal to 9. I'm going to solve each equation. Again, it's a standard kind of trick. I'm going to try and solve each equation for 2 lambda and plug in, see what happens. We might get lucky. Yz over x, 2 lambda is, so 2 lambda is xz over 2y. I'm just trying. And then 2 lambda is xy over 4z. So I can equal in any order. So I can equal these two and maybe these two. It doesn't matter. That will eliminate lambdas and bring me down to 3 equations and 3 unknowns. So if I equal these two, I get yz over x is equal to xz over 2y, from where 2y squared z is equal to x squared z. Oh yeah, nice. And if I equal the other, so let me put the red star here, and then we do the blue star for the second pair. I have xz over 2y is equal to xy over 4z, from where I can write 4xz squared is equal to 2xy squared. And the first equation is going to give me that x squared. So I'll do the line again. So here's again the red star for the first equation. I have, when z divided by z is 1. So I have a relationship that x squared is equal to 2y squared. From the blue equation, I have that 2's canceled, x's are gone, z squared, so y squared is equal to 2z squared. And I still have the x squared plus 2y squared plus 4z squared is equal to 9. Wow, awesome, this is solved. Because this plugs here and then both of these plug in there and you're done. Nice. Well, actually, we can do, yeah, so this one plugs in first. It will be in terms of y, and then in the next stage, so we still have y squared equals to 2z squared on ice. This becomes 2y squared plus 2y squared plus 4z squared equals to 9, which is actually 4y squared. So I'm going to copy the first one and get 4y squared plus 4z squared equals to 9. And now that one plugs in. I get 8, right? 2 times 2 is 4, 8, yep. So 8y squared plus 8z squared, oops, z squared plus 4z squared is equal to 9. So I get 12 z squared is equal to 9, from where z squared is equal to divide by 3 quarters. So z is plus minus root 3 over 2. So I got z. Is that a problem? It's no problem because this was actually fairly straightforward. You'll see when you try some of the other ones. Like, I don't think it can go any smoother than this. And x. Yeah, it's gonna be epic. So y squared is 2z squares. So y squared is equal to 2z squared, which is 3 halves, right? 2z squared, which is, we know that z squared is 3/4. So when you do times 2, it will just cancel, so it's 3 halves. And then y is plus minus root 6 over 2. Nice. Nice. So far I have z, I have y, and now I need x's. So where's the single equation that says x equals everything else? There it is, 2y squared. So x squared equals 2y squared. Now we know that y squared is 3 halves. 2 times 3 halves, so that's just 3. So x is root plus minus root 3. Awesome. We have 7 minutes, which is enough to write the combinations of points.
For y, I got root 3 over 2, but I got the other two right.
If it's a square root of, right? If it's a square root of this, then it's a square root of 3 divided by square root of 2, and then I have square root of 2 as square root of 2. So that's a 2, and that's root 6 on top.
No, I just had the root 3 over right here.
Why? If you start from here,
I did it completely different way.
oh, so let's see. We start with root 3 over 2, root 6 over 2. So they're all positive? No, I switched them. This is 6 for y, and this is 3 for z. Root 3, root 6 over 2, negative root 3 over 2. Yeah, you get the idea, right? Awesome. Root 3? No. We are all in this suffering together. Negative root 6 over 2, negative root 3 over 2. So we have that one, that one, that one. We all good? And now another 4 with negative root 3, which is, you just copy what you have with negative root 3. No, pen, wake up. Not now. Did you just say yes? I have 4 minutes. I have to use it. I have to finish this. You have to have 8. Oh, we're almost there. All right, now we find D. And there they are. So it's awesome, right? If you're still trying to visualize this, just take a stencil, right? Hit it in a dough, and then whatever the peaks and the valleys are of the dough that is touching the stencil, those are the min and the max values that you are detecting using this method. All of the other min and max values that are inside, that are not touching the stencil, are the ones that are detected by 12.8. fx equal to 0, fy equals to 0, and then crank the procedure for that. You want to know which one is min, which one is max? Crank the D. Just do it 8 times, not a big deal. And yeah, you have, I guess, tomorrow to enjoy all of this stuff. On Wednesday, we are going to do another example, 12.8, another example from Lagrange, and then push into chapter 13, do some double integrals. I know, you would say that the single integral was a problem.